Hi, my name is Jordan Gillard, and this is my presentation on Terraform and Infrastructure as Code. Before we get into how Terraform works, I want to talk about the problem Terraform addresses. I will begin with a quote by Yevgeny Brickman from Terraform Up and Running 2nd edition. A long time ago, in a data center far, far away, an ancient group of powerful beings known as sysadmins used to deploy infrastructure manually. Every server, every database, every load balancer, and every bit of network configuration was created and managed by hand. It was a dark and fearful age. Fear of downtime, fear of accidental misconfiguration, fear of slow and fragile deployments, and fear of what would happen if the sysadmins fell to the dark side, i.e. took a vacation. There's a lot we can take away from that quote. Manually deploying infrastructure is slow, error-prone, and fragile. However, thanks to the DevOps movement, there's an alternative. This alternative is IAC, or Infrastructure as Code. The idea behind Infrastructure as Code is that you write and execute code to define, deploy, update, and destroy your infrastructure. There are many IAC tools on the market, but Terraform is among the best. Terraform allows you to deploy your code using a simple, declarative language and quickly deploy all your company's infrastructure to public and private cloud providers with one command. Let's look at a simple example. How might I deploy a single server on AWS? Well, first, I'll start by writing the following code in a special .tf file. We might name this file main.tf. I'll tell Terraform which cloud provider I'd like to use and which region by that provider I'd like my server in. In this case, I'll be using Amazon Web Services as my cloud provider and US East 2 as my region. Next, I'll tell Terraform which resources I would like provisioned. I only want a small server or AWS instance that will be named example, with a cryptic looking AMI or Amazon machine image. That funny looking word denotes an Ubuntu operating system. And a T2 micro instance. T2 instances are low cost general purpose servers with low CPU and memory. And then I'll run the following commands in my terminal. Terraform init and Terraform apply. It's that easy. Terraform will communicate with Amazon Web Services and create a T2 micro-sized AWS EC2 instance in the US East 2 region. Okay, so you just saw how easy it is to deploy something with Terraform, but you might be asking yourself, how does Terraform play into the entire IAC ecosystem? Aren't there already a bunch of other tools like Kubernetes, Docker, or Ansible? What's the difference? These are great questions because it's not immediately clear which tools do what. We can classify IAC tools into 5 broad categories. The first category is ad hoc scripts. Using ad hoc scripts is a straightforward approach. You choose a scripting language like Bash or Python and write some code to automate whatever you were doing manually. Then you execute that script on your server. Here's a super simple Bash script for installing Nginx on a Linux server. The script installs the EPEL repository, then the script updates the repository, and finally the script installs Nginx. The next category of infrastructure as code tools are tools for configuration management. These are tools for installing and managing software on existing servers. Keyword existing. They do not create new infrastructure, but instead manage what you already have. Some examples might include Ansible, Puppet, or SaltStack. Here's an example of a Puppet manifest, which installs and runs an Apache web server. We start by updating the app package manager. Then we tell Puppet to ensure that the server installed Apache after the apt update command runs. And then we tell Puppet to ensure that the Apache service is running. So what is the benefit of using a configuration management tool over ad hoc scripts? Well, for one, configuration management tools force developers to use specific coding conventions. Every developer can write an ad hoc script differently, but configuration management tools force us to uphold certain standards. These might include how we organize our files, name parameters, or manage our secrets. The next benefit is idempotence. Idempotence means that when we run a configuration management tool multiple times, it won't make any difference than if we ran it just once. So what does this mean? Well, you can apply the same Puppet manifest on a server 1 time or 1,000 times, and the state will be the same. This behavior is not possible with ad hoc scripts unless you want to add a bunch of code that checks certain conditions. The final benefit is distribution. Ad hoc scripts run on one machine. Developers design configuration management tools to manage massive amounts of remote servers. Not only that, but configuration management tools can work with all of these remote servers in parallel. So no matter how many servers you have, these tools can update all of them at once. The third category of infrastructure as code is server templating tools. These include Packer, Docker, and Vagrant. These have been growing a lot in popularity and are an alternative to configuration management tools. Here's the gist of them. Instead of creating servers and running code on each one, you can instead generate an image of an operating system that captures all of the software, files, and state in a single snapshot. These tools play well with other infrastructure as code tools that could install these server templating images on servers for you. There are two categories for working with server templating tools. The first is containers. Containers emulate a single user space of an operating system and run on top of a container engine, like the Docker daemon. Containers are excellent because they run in isolation. They have their own processes and memory, so they are nicely isolated from other processes on the host machine. However, one bad thing about containers is that they have to share the server's hardware with other containers, so they aren't as isolated or secure as virtual machines. Containers must communicate with the daemon they run on top of to be allocated their server's resources. The benefit of containers over virtual machines is that they can boot up quickly and have less overhead. On the other hand, a virtual machine emulates an entire system, meaning both the operating system and computer hardware. VMs run on top of a hypervisor and virtualize all of their underlying hardware, CPU, etc. They are completely isolated from other virtual machines and the server they run on. They run the same in all environments. One downside of VMs to containers is that they require more of the computer's resources than containers and much longer to start up. Here's a nice diagram from Terraform up and running. We can see the virtual machines on the left running on their hypervisor, with their own virtualized hardware and guest operating systems. On the right, we can see containers with their virtualized user space running on their container engine. One last note about server templating tools. Tools like Packer and Docker serve slightly different purposes. Packer is usually used to create operating system images. Remember that funny looking AMI we saw in the Terraform example in the beginning of this slideshow? Packer could be used to generate that machine image. Then we could use Docker on top of that operating system to run a specific application. Both of these tools are nice examples of ways to create immutable infrastructure. The idea here is that once you deploy something, you never change it. If you want to change, you make a new image and deploy it on the server. Because state doesn't change, you are less likely to get hard to understand bugs caused by configuration drift. Okay, we're almost to the end of infrastructure as code tools, I promise. The next one we will cover is orchestration tools. Orchestration tools include Kubernetes and Docker Swarm. The server templating tools we just looked at are great for creating containers and virtual machines, but orchestration tools are for managing them. These kinds of tools allow us to monitor our existing services, distribute traffic amongst those services, quickly scale our services in response to load. They also allow us to easily roll out updates to our software by bringing down existing instances and booting up new ones. The final category of IAC tools is provisioning tools. Examples of provisioning tools are Terraform and Amazon Web Services CloudFormation. All the previous tools we looked at are for defining code that runs on an individual server. But how do we create the servers themselves? As a matter of fact, you can use tools like Terraform to generate more than just servers, but also load balancers, databases, or any other part of your infrastructure. Here's a simple diagram I made. This diagram shows Terraform getting a configuration file, and from that provisioning compute, storage, NoSQL database, and routing services on Amazon Web Services. Now that we covered all the different categories of infrastructure as code, I want to pose a question. How might you use 3 of the different categories of infrastructure as code together to manage your deployments? Take 15 seconds to think about which ones you might combine. Remember, the 5 different categories are ad hoc scripts, configuration management tools, server templating tools, orchestration tools, and provisioning tools. Okay, now that you thought about it, what did you come up with? There's plenty of different answers. One might be using a server templating tool to create a base operating system. Then, you use Terraform to make all of your servers which use that base operating system, and use an orchestration tool like Kubernetes to deploy containers on those servers. Let's dive a bit deeper. How does Terraform work? Terraform is an open source tool that runs on your local machine using a binary compiled from the Go programming language. It was initially released 6 years ago from this writing, on July 28, 2014 by HashiCorp. You do not need to use anything other than the binary to make Terraform work. This is because under the hood, Terraform makes API calls to cloud providers like Amazon Web Services or Microsoft Azure, and tells those providers what to do to get your infrastructure up and running. So, how does Terraform know what API calls to make? It does this by leveraging your Terraform configuration files. Remember that script from the beginning of this presentation? We fill configuration files with code like that, which Terraform turns into API calls. And that's it. Your entire infrastructure can be declared in Terraform configuration files and kept in a version control system like Git. Whenever you want to change your infrastructure, you no longer need to click around an online cloud provider's dashboard. You only need to update a Terraform configuration file. The fact that you can store these files in version control means you get a history of your infrastructure, making it easy to track down precisely what you have running and helping you see changes that might have resulted in bugs. I hope I gave you an excellent high-level view of infrastructure as code and Terraform's place in it. If you are interested in learning more, I recommend Terraform Up and Running, Writing Infrastructure as Code by Yevgeny Brickman.